Welcome to the deep dive. Today, I want you to picture something we interact with constantly. Fluids on the move. Think about your garden hose filling a bucket, maybe. Or even the really complex, unseen systems that bring electricity to your home. What connects them all? Well, they're dynamic spaces where mass and energy are continuously flowing in and out.
Exactly. From the simplest faucet, to the most complex power generation plant, these systems are fundamentally governed by principles that dictate how mass and energy behave.
And that's our mission today. We're taking a deep dive into the core concepts of mass and energy analysis of control volumes. Our goal is to equip you with the understanding of how these principles allow engineers to analyze, design, and optimize systems where fluids are constantly entering and leaving. It's truly like uncovering the hidden mechanics behind so much of our modern world.
Yeah, and we're pulling our insights from a foundational textbook chapter that lays out these principles. We're focusing on the practical applications and, as you'll hear, some truly surprising insights that might challenge your intuition a bit.
Okay, let's unpack this, and we'll start with something that feels incredibly intuitive. The conservation of mass. It just makes sense, right? If you mix, say, 100 grams of oil with 25 grams of vinegar, you expect, what, 125 grams of dressing,
Mhm.
or like 2 kilos of hydrogen react with 16 kilos of oxygen, you get 18 kilos of water. Simple addition.
That intuition is absolutely correct for, well, the vast majority of our everyday experiences and for nearly all engineering applications. However, here's where it gets really interesting. On a fundamental physics level, mass isn't perfectly conserved. Albert Einstein's famous E-mem-Silic equation actually tells us that mass and energy can, in fact, be interconverted.
Wait, so my salad dressing, the mass isn't perfectly conserved. Does that mean my whole understanding of the universe needs, like, recalibrating?
Huh? Not at all. Your salad dressing is perfectly safe, don't worry. The insight here is understanding the incredibly small scale of that conversion. For instance, when 1 kilogram of water forms, it releases a significant amount of energy, about 15.8 megajoules. That's quite a bit. But that energy release corresponds to a mass change so infinitesimally tiny. It's like 1.76 times 10 to the minus 10 kilograms. Practically undetectable.
Wow. Okay, so negligible for salad dressing and for most engineering, too.
Exactly. So for our purposes, and indeed for almost all engineering scenarios, we can safely treat mass and energy as separate conserved quantities. It's really about knowing the boundaries of the models we use.
That distinction makes a lot of sense. So we're focusing on systems where mass can cross boundaries, which brings us to the core concept of a control volume. How does that differ from, say, a closed system?
Right. So in a closed system, like a sealed container, no mass can enter or leave. Its mass is constant. Simple. But a control volume is a defined region in space where mass can actively flow in and out. Think of it as drawing an imaginary boundary around a component you want to analyze, like a section of pipe, or a pump, or a turbine.
Got it. And if mass is moving, we obviously need ways to measure that flow.
Precisely. We primarily use two key terms here. First, mass flow rate, which we usually symbolize as m.m. That's the amount of mass flowing through a cross-section per unit time, typically kilograms per second.
Okay, m dot, kilograms per second.
And then there's volume flow rate, v dot v. That's the volume of fluid flowing per unit time, usually in cubic meters per second.
Right. Now, here's a crucial distinction, I think, that often surprises people, especially when dealing with compressible fluids, like air.
Yes, absolutely.
While mass flow rate is conserved in what we call steady flow, volume flow rate is not necessarily conserved. Can you give us an example where that really plays out?
Sure. A perfect example is an air compressor. Air enters at, let's say, a certain volume flow rate. It gets compressed, right? So it leaves at a much lower volume flow rate because it's denser now.
Ah, right. Density changes.
Exactly. But the mass of air entering per second is identical to the mass of air leaving per second, assuming steady operation. So m dot is constant, even though v dot changes dramatically.
That clarifies it perfectly. So at its heart, the mass balance equation for any control volume is pretty straightforward then.
It is. Basically,
Yeah.
whatever mass comes in minus whatever mass goes out equals the change in mass stored within that control volume.
Simple accounting.
Pretty much. In its most fundamental form, we write it as min amount mcv. And when we look at it as a rate, which is often more useful for continuous processes, it becomes imsin imminent, dmcv dt. That ddt just means the rate of change over time.
Okay. And for what we call a steady flow process, where conditions at any point within the system aren't changing with time, this equation simplifies beautifully, doesn't it?
It does, thankfully. For steady flow, the mass content of the control volume itself remains constant. So that change term, dmCv/dt, is zero,
Meaning?
meaning the mass flow rate in must simply equal the mass flow rate out, mc und out. Or if you have just one inlet and one outlet, like in a simple pipe, it's just mc1, mc2. It's the ultimate balanced budget for mass.
That makes perfect sense. And you see this principle everywhere, right? Like when you're filling that 10-gallon bucket with a garden hose, the amount of water going in dictates how quickly the bucket fills.
Exactly. Or, for a more counterintuitive example, think about emptying a tall water tank from a drain at the bottom. It actually takes significantly longer to empty the bottom half compared to the top half, even though it's the same volume of water.
Really? Why is that?
Because as the water level drops, the pressure pushing the water out decreases. Less pressure means lower discharge velocity. So the flow rate slows down considerably as the tank gets emptier.
Huh. That's a great example of the principle and how it affects rates. Okay, so we firmly established the principles of mass conservation in these flowing systems. Now let's turn our focus to the equally critical element, energy. How does energy flow along with these fluids? When we're talking about energy in flowing systems, there's this unique term called flow work.
Yeah.
What exactly is that?
Right, flow work. It's basically the work required to push a chunk of fluid into the control volume or push it out.
Yeah.
Imagine you have to physically shove that fluid across the boundary against the existing pressure. That takes work. Mathematically, it turns out to be simply the product of the fluid's pressure and its volume, PV.
Okay, pressure times volume. Got it. And here's where engineers get really clever to simplify things, apparently.
Yes, this is quite elegant, actually.
Instead of dealing with flow work as a separate term in energy equations, they combine it with the fluid's internal energy, that's the microscopic energy of the molecules,
Right.
to create a single convenient property called enthalpy, H. So HU plus PV. What's the genius in that combination?
The genius is that by using enthalpy, we automatically account for this flow work energy. It simplifies the energy balance for flowing systems immensely. It essentially bundles the energy needed to get the fluid into or out of the control volume right along with the energy the fluid already possesses internally.
Right.
Makes the math much cleaner.
Nice. So when we talk about the total energy of a flowing fluid, what are its components then, using this enthalpy idea?
Okay, the total energy of a flowing fluid, often denoted by the Greek letter theta, is the sum of three main parts. It's enthalpy, H, which we just discussed. It covers internal energy and flow work. It's kinetic energy, K, which is the energy due to its bulk motion or velocity, calculated as V22. And its potential energy, K, which is the energy due to its elevation in a gravitational field, calculated as G, where G is gravity and Z is height. So the full equation is enthalpy, kinetic, potential. And naturally, just as mass flows in and out, this total energy gets transported right along with it. Exactly. We express this energy transport as musky for the total energy carried by a specific amount of mass, or more commonly for flay rates, as mus to the rate of energy transport.
Now, you mentioned earlier, or it was in the source material, that the kinetic energy term is often negligible. Can you give us a sense of when it suddenly becomes critical? Not just high velocities, but what kind of systems absolutely rely on accurately accounting for it?
That's a great question. Context is key. For example, consider air flowing in a typical heating duct. The velocity might be, say, 5 or 10 meters per second. The kinetic energy term, V22, might represent less than 0.1% of the total energy being transported compared to the enthalpy. So, totally negligible. However, in devices specifically designed to change fluid velocity dramatically, like a nozzle.
Which speeds things up.
Right, or a diffuser, which slows things down. In those cases, the kinetic energy term becomes paramount. The whole point of those devices is often to convert between enthalpy, pressure, and kinetic energy. Ignoring there would give you completely wrong answers.
Right, okay, so it's all about the purpose of the device. That makes perfect sense. So we've got the foundational principles down, mass in, mass out, energy in, energy out, including that clever enthalpy term. Now let's turn our attention to the unsung workhorses of modern engineering, the steady flow devices you encounter every day, often without realizing they are perfect demonstrations of these very laws. What defines a steady flow device? Again, just to be clear.
Yeah, good to reiterate. In a steady flow device, conditions at any specific point within that device do not change with time. This implies that the mass inside the control volume and the energy inside the control volume remain constant. Think of a turbine running continuously, or a pump operating at a constant speed, or a heat exchanger with steady inlet conditions. Their internal state is stable over time.
Which brings us to the energy balance for steady flow. How does the first law of thermodynamics, energy conservation, translate into something practical for these continuous systems?
For steady flow, it simplifies beautifully. Since the energy stored within the control volume isn't changing, the rate of energy entering must exactly equal the rate of energy leaving. So, each in, X out. Simple balance.
Energy in equals energy out.
Okay. This means all forms of energy entering that could be heat transferred in, work done on the system, and the energy carried in by the mass and sound must equal all forms of energy leaving heat transferred out, work done by the system, and energy carried out by the mass. So that act out.
Got it. Let's break down the key terms in that energy balance. What's the role of heat transfer, QJ?
QJ represents the rate of energy added to or removed from the system as heat. For many devices that are well insulated or where heat transfer is inherently small compared to other energy terms, like large turbines or compressors, we often assume QJ is zero. We call those processes adiabatic.
Okay, adiabatic means no heat transfer and work, WH. I'm assuming this is distinct from that flow work we bundled into enthalpy.
Precisely. Good catch. This WH refers to other forms of work, primarily shaft work, the power produced by a turbine shaft, or the power consumed by a compressor or pump shaft. It could also include electrical work, like in an electric heater element immersed in the flow. And yes, crucially, flow work is already handled by the enthalpy term, H equals U plus PV, so we don't count it separately here.
Excellent clarification. And enthalpy change.
Ah, yes. The change in enthalpy between the outlet and inlet, I told him, is often the largest and most significant energy component in many steady flow systems. It represents the combined change in the fluid's internal energy and its flow work energy. Huge changes here often correspond to significant work or heat transfer.
Okay. What about the changes in kinetic energy and potential energy? We know kinetic energy can be critical sometimes.
Right. Kinetic energy change is indeed crucial at high velocities, particularly in those nozzles and diffusers we mentioned. But for many other devices, like heat exchangers or throttling valves, velocity changes are often small, so ache might be negligible. You need to check the numbers. A velocity of, say, 45 meters per second sounds fast, but its kinetic energy, V22, is only about 1 kilojoule per kilogram, which might be small compared to enthalpy changes in the hundreds or thousands.
And potential energy change.
For potential energy, it's almost always negligible for typical industrial devices, unless there's a really large elevation change involved. Think about it. To get a potential energy change of just 1 kJ/kg, you need an elevation difference of over 100 meters, about 330 feet. Most single components, like a turbine or a compressor, just aren't that tall. The main exception would be analyzing a system involving pumping fluid up to a very high reservoir, or maybe a hydroelectric power plant.
Okay. So we can often simplify the full energy balance equation by dropping terms like QJ or even OC, depending on the specific application and the relative magnitudes involved.
Exactly. Engineering analysis is often about knowing which terms are dominant and which are truly insignificant for the specific problem you're trying to solve. It makes the calculations much more manageable.
Right. You can even see this energy balance intuitively with something simple, like an electric hot water heater in your house. The electrical energy supplied, WHN, minus any heat losses from the tank to the surroundings, Q out, directly accounts for the increase in energy of the water stream as it flows through, which is mostly seen as an increase in its enthalpy. It all has to add up.
Precisely. It's a fundamental accounting principle for energy in these systems.
With those foundational principles of steady flow now clear, let's turn our attention to some specific devices. These are the workhorses, right? The components that make things happen. Let's start with nozzles and diffusers again.
Okay. Nozzles and diffusers, as we touched on, are fundamentally opposite in function, and they're classic examples where kinetic energy changes are paramount. A nozzle accelerates a fluid. It does this by converting the fluid's internal energy, or enthalpy, manifested often as pressure, into kinetic energy. So velocity goes up, pressure usually goes down. A diffuser does the opposite. It slows down a fluid, converting kinetic energy back into enthalpy, usually resulting in a pressure increase.
And in both, we usually assume heat transfer and work are negligible.
Generally, yes. The flow happens too quickly for significant heat transfer, and there's no shaft work involved. So the energy balance often simplifies to just enthalpy in plus kinetic energy in equals enthalpy out plus kinetic energy out, H1 plus V122 equals H2 plus V222.
And this leads to that fascinating insight you mentioned. In a diffuser, when you slow down fast-moving air, it can actually increase its temperature. How significant can that be?
It can be quite significant. It's a direct conversion of that macroscopic kinetic energy into microscopic internal energy. For example, air entering a diffuser at, say, 10 degrees C, but moving at 200 meters could easily exit at 30 degrees C or more after being slowed down substantially. That kinetic energy had to go somewhere. Conversely, if you have high-pressure steam accelerating through a nozzle, its temperature will drop significantly as its internal energy converts to kinetic energy, maybe from 300 degrees C down to 250 degrees C, for instance.
Wow. Okay, next up. Turbines and compressors. These are the power producers and power consumers in many, many systems.
Indeed. Turbines, whether they run on steam, hot gas, or water, like in hydroelectric dams, are devices designed to produce power output. They do this by extracting energy from a flowing fluid, causing a drop in the fluid's enthalpy. That energy comes out as rotating shaft work. Tell me about.
And compressors, pumps, fans.
They do the opposite. Compressors for gases, pumps for liquids, and fans for small gas pressure increases require power input, Wn, to increase the pressure and thus the enthalpy of a fluid.
For these devices, what are the common assumptions we can often make regarding heat, kinetic, and potential energy?
Okay, for most large turbines and compressors, heat transfer, Q, is often relatively small compared to the work term, especially if they're well insulated, so we might approximate them as adiabatic, Q0. Potential energy changes are almost always ignored. As we discussed, the devices just aren't tall enough usually. Kinetic energy changes can sometimes be significant, especially in turbines dealing with high velocities, but they're often still small compared to the very large enthalpy changes. So they might be disregarded in a first-pass analysis, but it's worth checking.
So the main energy transfer is work in or out, primarily balanced by the change in enthalpy.
That's usually the dominant effect, yes. For example, calculating the power input needed for an air compressor involves figuring out the enthalpy increase of the air, plus accounting for any heat loss. For a big steam turbine, the power output comes almost entirely from the massive drop in the steam's enthalpy as it expands through the turbine blades.
Makes sense. Moving on to throttling valves. These sound simple, maybe even mundane, but they hold a surprising secret about temperature, you said.
They are indeed deceptively simple in construction, but fascinating in their effect. Throttling valves are basically any kind of flow restriction. Could be a partially closed valve, a long capillary tube like in your fridge, or even a porous plug. Their purpose is to cause a significant pressure drop in the fluid without producing any work, W0, and usually with negligible heat transfer, Q0, and negligible kinetic energy changes, Q0.
So if WQ and delta KE are all zero, what does the steady flow energy equation tell us?
It tells us that the enthalpy change must also be zero. It's a calmed also be zero, a 2 H1 euro. So an ideal throttling process is isenthalpic. The enthalpy remains constant across the valve, H2H1.
Okay. Constant enthalpy. Now the temperature mystery. Why does throttling often cause a big temperature drop, like in refrigeration systems, but for ideal gases, the temperature actually remains constant? That seems contradictory.
It does seem counterintuitive, doesn't it? Here's the key. Enthalpy is HEU plus PV. For real fluids, like the refrigerant R134A used in air conditioners and refrigerators, internal energy and the PV term are related in complex ways. During throttling, the pressure P drops significantly. The specific volume V might increase. It turns out that for many real fluids below certain temperatures, for H to stay constant when P drops, the internal energy U must also decrease. And a decrease in internal energy means a drop in temperature. That R134A example might drop by over 50 degrees Celsius.
Okay, so U drops to keep H constant for real fluids.
Right. But for an ideal gas, there's a specific property. Its enthalpy depends only on its temperature, T. Internal energy U also depends only on T. So if an ideal gas undergoes a throttling process where H remains constant, its temperature must also remain constant. It's a direct consequence of the ideal gas model. The changes in U and PV perfectly cancel each other out temperature-wise.
Fascinating. So the type of fluid really matters there. Okay, next up, mixing chambers. These seem pretty straightforward, and we encounter them all the time, even in our homes.
They're very common and usually quite simple. Their function is just to combine two or more fluid streams into a single stream. Think of the T-elbow in your shower mixing hot and cold water, or injecting steam into water flow to heat it up. There's typically no work involved, WTO0, and they're often assumed to be adiabatic, Q0, unless designed specifically for heat exchange with surroundings. Kinetic and potential energy changes are usually negligible too.
So the core principles are just conservation of mass and energy.
Exactly. For mass, the sum of the incoming mass flow rates must equal the outgoing mass flow rate. There are thumbs out. For energy, the sum of the incoming energy flow rates, which is just mth for each stream usually, must equal the outgoing energy flow rate out there.
Then that's how you can figure out, for instance, the ratio of hot to cold water needed to get your desired shower temperature.
Precisely. If you know the temperatures, which lets you find the enthalpies of the hot and cold water and the desired final temperature, you can use the mass and energy balances to calculate the required ratio of the mass flow rates, like needing about twice as much 140 degrees F hot water as 50 degrees F cold water to get 110 degree F a shower, roughly.
Simple, yet practical. Building on that idea of fluids exchanging heat, but maybe without mixing, let's look at devices specifically designed for that. Heat exchangers.
Right. Heat exchangers are crucial in countless applications, from power plants and chemical processes to your car's radiator and your home's air conditioner. Their job is to transfer heat between two fluid streams that do not mix. Examples include shell and tube exchangers, or simple concentric pipes where one fluid flows inside and the other flows in the annulus around it. Like mixing chambers, they typically involve no work, W2AO, and negligible kinetic and potential energy changes for each fluid stream.
What's particularly insightful here, according to the source, is how the rate of heat transfer, huge, depends on how you define your control volume. Can you explain that?
Yes, this is a really important point for analysis. Let's say you have hot oil cooling down and cold water heating up as they pass through the exchanger. If you draw your control volume around the entire heat exchanger and assume it's perfectly insulated from the outside world, then the net heat transfer for that overall control volume is zero. QH overall equals zero. Heat is just transferred internally between the two fluids.
Okay, overall, no heat in or out.
But if you draw your control volume around only one of the fluid streams, say just the cold water passage, then QH for that control volume represents the rate of heat transferred from the hot oil to the cold water. Similarly, if your control volume is just the hot oil passage, QH will be negative, representing heat leaving the oil. The magnitude of QH is the same in both single fluid analyses. It just represents heat entering one and leaving the other.
Ah, I see. So it's about perspective and what question you're trying to answer. You use the overall view to relate the streams and the individual view to find the heat transfer rate between them.
Exactly. For instance, you could analyze the water stream to find QH and then use that same QH value with opposite sign in the energy balance for the oil stream.
Very useful. Finally, for steady flow devices, let's briefly touch on pipe and duct flow.
Sure. Well, maybe not a distinct device like a turbine. The transport of fluids through simple pipes and ducts is fundamental. The key things to consider here are potential pressure drops due to friction, which is related to thermodynamics, but often handled with fluid mechanics equations, and importantly, heat transfer. Especially over long distances or in uninsulated pipe ducts, heat gains from or losses to the surroundings can be significant. QH is not zero. You can also have work interactions. Think of an electrical resistance heater, WHN, placed inside a duct to heat air, or a fan or pump, WHN, located along the pipe to overcome pressure drop or increase pressure.
Right, like in an electric baseboard heating system or a forced air furnace. You have electrical work going in as heat, but you also might lose some of that heat from the ducts before the air reaches the room. You need to account for that QH less in the energy balance to accurately predict the final air temperature.
Precisely. The steady flow energy equation provides the framework to analyze all these effects.
Okay, that covers the predictable world of steady flow pretty thoroughly. Now let's shift gears to the perhaps less predictable realm of unsteady flow processes. These sound a bit more dynamic, maybe even chaotic.
They can be, or at least their analysis is inherently more complex because things are changing with time. Unlike steady flow, where properties at a point are constant, in unsteady flow or transient processes, properties within the control volume itself change over time. Classic examples include charging an initially empty tank with a gas, draining a tank, inflating a tire, or even the startup or shutdown phases of devices that normally operate steadily. Cooking in a pressure cooker before it reaches steady pressure is also unsteady.
That sounds like it could get complicated quickly. Is there a common simplification used here?
Yes, a very useful one is the uniform flow assumption or idealization. This assumes that the properties of the fluid crossing the control volume boundary at the inlets or exits are uniform across the opening and remain constant, or can be reasonably averaged, throughout the entire duration of the process. This simplifies the integration over time that would otherwise be needed. It lets us analyze the process based on the initial and final states within the control volume and the total amounts of mass and energy that have crossed the boundary.
Okay, so we look at the beginning state, the end state, and the total stuff that moved across the boundary. How do the mass and energy balances look then?
They look similar to the rate forms, but integrated over the time of the process. For mass, it becomes mass in Massoud, change in mass within CV, or min mount equals m2 min 1 CV. For energy, it's energy out, change energy within CV. The energy terms include heat, work, and the energy transported by mass. So it looks like kin plus win plus minthin, crop plus walt plus net without, E2 E1 CV, where E is the total energy, internal plus kinetic plus potential, stored within the control volume.
That seems manageable with the uniform flow assumption. And this leads to one of the most classic, maybe counterintuitive, aha, moments in thermodynamics, charging an initially evacuated rigid tank with steam from a high-pressure supply line. The surprising result is that the steam inside the tank, once the valve is closed, ends up being hotter than the steam in the supply line it came from. Why on earth does that happen?
This is a fantastic example. It seems totally wrong at first glance, right? Here's the key. Remember that enthalpy H includes both internal energy and flow work, PV. The steam in the supply line has enthalpy H line. When that steam enters the tank, it has to push its way in, effectively carrying that PV energy with it. But once it's inside the rigid tank and comes to rest, it's no longer flowing in the same sense. So that PV flow energy associated with crossing the boundary gets converted.
Converted into what?
It gets converted primarily into internal energy of the steam now sitting inside the tank. So the energy balance for filling an evacuated, insulated, rigid tank simplifies essentially to the min H line equals N2U2, where M2 min. Yeah. This means the final internal energy of the steam in the tank is equal to the enthalpy H of the steam in the supply line. Since HU plus PV, and PV is always positive, this means U2 in the tank must be greater than U line in the supply line. And for steam, higher internal energy means higher temperature.
Wow. So the energy it used to push itself in gets trapped inside as extra internal energy, making it hotter.
Exactly. The flow energy gets converted into thermal energy once the flow stops within the control volume. It's a really neat consequence of the first law applied to unsteady flow.
That's a concept that really makes you stop and think. And once you grasp it, you probably start seeing implications elsewhere.
You do. This fundamental idea helps explain why inflating a tire can make the tire feel warm, even if the air from the pump feels cool. It helps us understand how pressure cookers reach high temperatures by trapping enthalpy, or even aspects of rocket propellant combustion in transient phases. It really is a powerful and universal principle.
And just like that, wow, we've journeyed through the fundamental principles of mass and energy analysis for flowing systems. It's quite a landscape. We went from the basic, almost obvious idea of mass conservation to the incredibly nuanced reality hinted at by Einstein's E=mc², even though we usually ignore it in practice.
Right. And the elegance of using enthalpy, HU plus PV, to automatically account for flow work, really simplifying the energy calculations for these open systems.
We also explored how kinetic energy and that flow energy can manifest in really surprising ways, like causing significant temperature changes in nozzles or diffusers, or that tank filling example.
Yeah, and we saw how these principles systematically govern the predictable workhorses of engineering: turbines, compressors, pumps, heat exchangers, throttling valves, allowing us to analyze and design them effectively using the steady flow energy balance.
And we didn't shy away from the dynamic world of unsteady flow processes, diving into that fascinating aha moment of the tank charging up hotter than its source. It shows how these principles apply even when things are changing.
Absolutely. And all this, well, it raises an important question for you, the listener. How do these principles, which are often hidden in plain sight, govern so much around us?
Yeah, think about it. Everything from the simple act of turning on a faucet or using a refrigerator, right up to the massive power systems that light our cities, they all rely on these fundamental flows of mass and energy. We've hopefully given you the lens today. So the final thought is, what other everyday systems can you now see, maybe a little differently, through this powerful lens of mass and energy analysis?